In the heart of our galaxy, hidden beyond clouds of cosmic dust and swirling stars, lies one of the greatest mysteries of the universe, a supermassive black hole. An object so powerful, so enigmatic, that it bends the very fabric of space and time. A region where the laws of physics, as we know them, break down, and nothing, not even light, can escape its grasp. For centuries, humanity has looked to the night sky, wondering what lies beyond the shimmering constellations. Ancient civilizations saw celestial gods and mythical creatures, while modern astronomers see something far more astounding: a singularity, a void of infinite density. But what exactly is a black hole? How did it come to exist? And what role does it play in shaping the very galaxy we call home? The idea of a black hole was once a mere mathematical curiosity, a thought experiment born from the mind of Albert Einstein. But today, we know that these objects are real, and the one lurking at the center of our Milky Way, Sagittarius A asterisk, is over 4 million times the mass of our Sun. Its immense gravity shapes the motion of countless stars, dictating the dance of the galactic core. But despite its influence, this black hole remained hidden for decades, an invisible giant lurking in the shadows. That is, until recent breakthroughs allowed us to capture its first-ever image, a feat once thought impossible. This is a journey into the unknown, a journey to uncover the secrets of the cosmic abyss, to explore the invisible forces that sculpt galaxies and challenge our understanding of reality itself. So join us as we venture into the depths of space, to witness the heart of darkness at the center of our own Milky Way. Welcome to the story of Sagittarius A asterisk, the black hole at the center of our galaxy. The story of black holes begins long before we had the tools to see them. It starts with a question as old as astronomy itself. What happens when a star dies? In the late 18th century, long before Einstein's revolutionary theories, English scientist John Michel and French mathematician Pierre-Simon Laplace speculated about the existence of dark stars, objects so massive that their gravitational pull would be too strong for even light to escape. At the time, it was little more than a theoretical exercise. No one could have imagined that such objects actually existed. Then, in 1915, Albert Einstein unveiled his groundbreaking theory of general relativity, forever altering our understanding of gravity. Instead of an invisible force pulling objects together, Einstein described gravity as the warping of space-time itself. The greater the mass, the greater the curvature of space. Just a year later, physicist Carl Schwarzschild took Einstein's equations a step further, describing what we now call the Schwarzschild radius, the point where gravity becomes so strong that nothing, not even light, can escape. A singularity, a black hole. But for decades, black holes remained an abstract concept. Many scientists doubted that such extreme objects could exist in the real universe. It wasn't until the mid-20th century, with the rise of powerful telescopes and radio astronomy, that the first indirect evidence began to emerge. In the 1960s, astrophysicists Jocelyn Bell Burnell and Annie Hewish detected mysterious, rapidly spinning neutron stars, pulsars, suggesting the existence of compact, high-gravity remnants of dead stars. Around the same time, scientists discovered Cygnus X-1, a powerful X-ray source 6,000 light-years away. It became the first widely accepted black hole candidate, providing the first real-world evidence that such objects weren't just theoretical. Theoretical physicist Stephen Hawking further revolutionized our understanding of black holes, proving that they weren't entirely black at all. His work on Hawking radiation suggested that black holes slowly evaporate over time, a concept that continues to challenge physicists today. But even as evidence grew, one question remained unanswered. If black holes exist, should there not be one at the center of our own galaxy? By the 1990s, astronomers turned their attention to Sagittarius A asterisk, a mysterious and powerful radio source at the core of the Milky Way. Using high-powered telescopes, researchers observed something incredible: stars whipping around an invisible point at mind-boggling speeds, some completing an entire orbit in just a few years. The only explanation? A supermassive black hole. It would take decades of technological advancement and international collaboration to finally bring this cosmic giant into focus. But in 2019, history was made when astronomers captured the first ever image of a black hole, an achievement that paved the way for an even greater challenge: imaging the one at the heart of our own galaxy. For decades, scientists suspected the presence of a supermassive black hole at the heart of our galaxy. But how do you study something that, by definition, emits no light? The answer lies in its gravitational influence and the light it bends around itself. The evidence: watching stars dance around the invisible. The key to confirming the existence of Sagittarius A asterisk was watching the motion of stars near the galactic center. In the 1990s, two independent research teams, one led by Reinhard Genzel and the other by Andrea Ghez, began tracking the orbits of individual stars around the Milky Way's core. The most striking discovery was S2, a star that orbits Sagittarius A asterisk in just 16 years. At its closest approach, S2 moves at over 25 million kilometers per hour, faster than any other known star. Such speeds could only be explained by the presence of a black hole 4 million times the mass of our Sun. In 2020, Genzel and Ghez were awarded the Nobel Prize in Physics for their groundbreaking work, proving that a supermassive black hole truly lies at the heart of our galaxy. Imaging the unseeable, the first ever picture of a black hole. Despite overwhelming evidence, a direct image of Sagittarius A asterisk remained elusive. Black holes, after all, are invisible, but they do cast a shadow. In 2019, an international collaboration known as the Event Horizon Telescope, EHT, made history by capturing the first ever image of a black hole, the now famous glowing ring surrounding the supermassive black hole in the galaxy M87. This stunning achievement set the stage for an even greater challenge: imaging our own galactic black hole, Sagittarius A star. By linking telescopes across the world, from Hawaii to Antarctica, the EHT team created a virtual telescope powerful enough to resolve details the size of a golf ball on the moon. However, unlike M87's black hole, which is a monstrous 6.5 billion times the Sun's mass, Sagittarius A asterisk is much smaller, making it harder to capture. The breakthrough: revealing Sagittarius A asterisk. After years of data processing, in May 2022, astronomers finally unveiled the first ever image of Sagittarius A star. It looked eerily similar to M87's black hole, a glowing ring of superheated gas circling an empty void. But this wasn't just a photograph. It was proof that black holes follow Einstein's predictions, even under the most extreme conditions. The anatomy of a black hole: what lies beyond the event horizon. So, what exactly happens inside a black hole? A black hole is defined by its event horizon, the point of no return. Anything that crosses this boundary, whether a planet, a star, or even light itself, is lost forever. At the center lies the singularity, a point of infinite density where the known laws of physics break down. Einstein's equations predict that space and time themselves collapse here, creating one of the greatest mysteries in modern physics. Physicists have long struggled to reconcile general relativity, which describes gravity on cosmic scales, with quantum mechanics, which governs the subatomic world. Black holes sit at the crossroads of these two fields, hinting at a deeper, unified theory of the universe. How black holes shape the universe. Despite their ominous reputation, black holes are not just cosmic vacuum cleaners sucking up everything in their path. In fact, they play a vital role in galactic evolution. Galactic architects. The immense gravitational pull of black holes helps structure galaxies, influencing star formation and the distribution of matter. Quasars and jets. Some black holes power the most energetic objects in the universe. Quasars, which shine brighter than entire galaxies, and relativistic jets, which blast matter across intergalactic space. Time machines. Due to extreme gravitational time dilation, an observer falling into a black hole would experience time slowing down relative to the outside universe. In theory, black holes could provide insight into time travel and the nature of spacetime itself. As we continue to unlock the secrets of black holes, we're left with even bigger questions. What happens to the information that falls into a black hole? Could black holes lead to parallel universes? And could they hold the key to understanding the very origins of space and time? For centuries, black holes were the realm of theory, enigmatic voids lurking at the edges of our understanding. But today, they are no longer just mathematical abstractions. They are observable, measurable, and deeply influential in shaping the cosmos. The discovery and imaging of Sagittarius A was a monumental achievement, but it was only the beginning. Scientists are now racing to answer new, profound questions about these cosmic titans, refining the image beyond the first glimpse. While the Event Horizon Telescope, EHT, provided the first-ever image of Sagittarius A*, the resolution was limited. Unlike the relatively stable black hole in M87, Sagittarius A* is much more dynamic. The swirling plasma around it changes on timescales of minutes, making it harder to capture a single, clear snapshot. To improve the resolution, scientists are now expanding the EHT network with more telescopes and more precise instruments. Future observations will reveal real-time videos of matter spiraling into the event horizon, giving us an unprecedented look at the violent forces at play. Probing the physics, general relativity versus quantum mechanics. Despite the success of Einstein's general relativity in predicting the behavior of black holes, there are still gaps in our understanding. General relativity describes black holes as infinitely dense singularities, but quantum mechanics suggests that information cannot be destroyed. Hawking radiation, proposed by Stephen Hawking, implies that black holes slowly evaporate, but how this process works remains a mystery. The information paradox, a fundamental puzzle, questions whether information that falls into a black hole is lost forever or somehow preserved. To address these challenges, physicists are exploring theories such as quantum gravity and string theory, which attempt to unify general relativity with quantum mechanics. Some theories propose that black holes could be holographic projections or even gateways to other dimensions. Supermassive black holes and the evolution of galaxies. Sagittarius A* isn't just an isolated object. It plays a crucial role in the evolution of the Milky Way. Observations suggest that supermassive black holes and galaxies co-evolve, meaning their growth is interconnected. Black hole mergers, driven by galactic collisions, may trigger bursts of star formation or quench star formation entirely. The Milky Way Andromeda collision, set to happen in about 4.5 billion years, could result in a much larger black hole at our galactic center. By studying Sagittarius A*, scientists hope to uncover the broader role of black holes in shaping the large-scale structure of the universe. New tools for exploration, next-gen telescopes, and space missions. The next decade will usher in a new era of black hole research, powered by cutting-edge observatories and space missions. The James Webb Space Telescope, JWST, is already providing deep infrared views of the galactic core, helping us study black hole accretion disks and surrounding dust clouds. The Square Kilometer Array, SK, set to be the most powerful radio telescope ever built, will map the formation of early black holes in unprecedented detail. Future space missions like LISA, Laser Interferometer Space Antenna, will detect gravitational waves from colliding black holes, offering new ways to observe these enigmatic objects. The search for the unknown, exotic black hole theories. As technology advances, so do the questions. Could some black holes be primordial, formed in the early universe before stars even existed? Do naked singularities, where space collapses without an event horizon, actually exist? Could some black holes harbor wormholes, linking distant parts of the universe? These questions push the limits of our understanding, challenging the very fabric of physics. The discovery of black holes has reshaped our understanding of the universe. But for all we have learned, the greatest mysteries remain unsolved. What lies beyond the event horizon? Can we ever fully understand the physics of the singularity? And could black holes hold the key to unlocking the fundamental nature of reality itself? The future of black hole research is more exciting than ever, driven by new technologies, ambitious space missions, and groundbreaking theories that could redefine our place in the cosmos. Building a better picture, the next generation of telescopes. Capturing the first image of Sagittarius A asterisk was just the beginning. Scientists are now working to create real-time movies of black holes in action, revealing how matter falls into the event horizon and how these cosmic giants evolve over time. The next generation Event Horizon Telescope, ENIHD, will use space-based radio telescopes to dramatically improve resolution, allowing us to see the fine details of black hole dynamics. The upcoming Lynx X-ray Observatory will probe high-energy interactions near event horizons, helping us understand how black holes feed and grow. With these new tools, we may finally uncover the true nature of the extreme environments surrounding black holes. Gravitational waves, listening to black holes collide. Until recently, black holes were silent, invisible giants that could only be inferred through indirect observations. But with the advent of gravitational wave astronomy, we can now listen to black holes colliding. The LISA mission, Laser Interferometer Space Antenna, launching in the 2030s, will detect gravitational waves from merging supermassive black holes across the universe. These signals will allow us to map black hole mergers over cosmic time, tracing the formation of galaxies billions of years ago. Each new detection brings us closer to answering fundamental questions. How do black holes grow? How often do they merge? And could these collisions produce entirely new forms of matter or energy? The quest for the theory of everything. Black holes are more than just celestial objects. They are cosmic laboratories for testing the most extreme physics in existence. Einstein's general relativity describes black holes on large scales, but breaks down at the singularity. Quantum mechanics governs the microscopic world but struggles to explain gravity. A true theory of quantum gravity, a theory of everything, must unify these two realms. Some scientists believe that black holes might be the key to this missing theory. Could space-time itself be made of quantum information? Could black holes be holograms? These questions challenge the very foundation of physics. Exotic possibilities. Black holes, wormholes, and parallel universes. While Einstein's equations predict black holes, they also allow for wormholes, hypothetical tunnels through space-time. If wormholes exist, they could serve as shortcuts across the universe or even gateways to parallel dimensions. Other radical ideas suggest that black holes might be portals to new universes, with each black hole in our cosmos birthing a separate reality on the other side. These ideas remain speculative, but the more we learn about black holes, the more we realize how much we don't know. What happens next? The coming decades will be a golden age for black hole research. With new telescopes, deep space probes, and gravitational wave observatories, we are on the brink of revolutionary discoveries. One thing is certain. The deeper we look into the darkness of black holes, the closer we come to unlocking the ultimate secrets of the universe itself. For centuries, black holes existed only in the minds of theorists, mathematical ghosts haunting the edges of physics. Today, they are real, observable, and more mysterious than ever. The journey to understand Sagittarius A asterisk has been one of humanity's greatest scientific achievements. From the first mathematical predictions to the historic images captured by the Event Horizon Telescope, We have come closer than ever to deciphering the secrets of these cosmic enigmas. But black holes are more than just objects of scientific curiosity. They shape the universe, guiding the evolution of galaxies, influencing the birth of stars, and challenging our understanding of space-time itself. And yet, for all we know, the biggest questions remain unanswered. What happens at the singularity? Can black holes lead to new dimensions or even new universes? Could they hold the key to a deeper, unified theory of reality? The next frontier of exploration awaits. Future telescopes, space missions, and breakthroughs in quantum physics will bring us closer to answers. But perhaps the greatest discovery lies not in what we already know, but in what we have yet to even imagine. The universe is vast, mysterious, and full of wonders yet to be revealed. And at its core, the black hole of Sagittarius A asterisk reminds us that some of the greatest discoveries lie not in what we can see, but in what we dare to explore.